Assalamu alaikum everyone. I am Wasif Ahmed from the discipline of BS Biotech with ID 024. The topic of our presentation is AFM, stand for Atomic Force Microscopy. First of all, background of AFM. The AFM was invented by IBM scientists in 1985. The precursor to the AFM, the scanning tunneling microscope, STM, was developed by Gerd Binning and Heinrich Rohrer. In the early 1980s, at IBM Research Zurich, a development that earned them the 1986 Nobel Prize for Physics. The first AFM instrument built by Benning-Quet and Gerber, the STM, with a lever made by carefully gluing a tiny diamond onto the end of a spring made of a thin strip of gold. This was the cantilever of the first AFM. What is AFM? AFM stands for Atomic Force Microscopy is a powerful technique that enables the imaging of almost any type of surface, including polymers, ceramics, composites, glass, and biological samples. AFM is used to measure and localize many different forces, including adhesion strength, magnetic forces, and mechanical properties. It is an instrument used for the study of surface property for both conductive and non-conductive samples. AFM is able to build three-dimensional maps of surface properties in any type of surface. Below is the diagram of AFM, which tells us about AFM technique like probe of AFM on sample surface to imagine the surface property of the sample. Next is the principle of AFM. Principle of AFM is that this nanoscale tip is attached to a small cantilever which form a spring. As the tip contacts the surface, the cantilever bends, and this bending is detected using a laser diode and a split photo detector. This bending is indicative of the tip sample interaction force. Unlike the electron microscope, which provides a 2D projection or a 2D image of a sample, AFM provides true 3D surface profile. Mainly three basic modes: contact mode, non-contact mode, and tapping mode. First of all, contact mode. In the contact mode, the AFM tip is continuous contact with the surface. The contact mode is only used for specific applications such as force curve measurements. Non-contact mode signal to noise benefits associated with modulated signal. Oscillating modes can measure images with a small probe sample force. Tapping mode. In the tapping mode, the AFM cantilever is vibrated above the sample surface such that the tip is only in intermittent contact with the surface. This proper helps to reduce shear forces associated with the tip movement. The tapping mode is the recommended mode that is commonly used for AFM imaging. Unlike the electron microscope, which provides a 2D projection or 2D image of the sample, AFM provides a true 3D surface profile. Here is a chart of modes of operation in AFM, like mode of operation: contact mode, non-contact mode, and tapping mode, and force of attraction, like contact mode strong, repulsive, and non-contact mode weak, attractive, and tapping mode strong, repulsive. And the force of interaction in contact mode: constant force or high, constant high. And the non-contact mode weak, attractive. Force of interaction in this mode is vibrating probe. And third is tapping mode: strong, repulsive, and force of interaction is vibrating probe. In this graph, three modes of AFM is explained via graphs, and the force is at y-axis and tip sample separation at x-axis. And the three modes of AFM is defined in this graph. Next is the working of AFM. In working of AFM, there are some modes used in the working of AFM, like first is detection mode. A laser beam in detection mode, a laser beam is used to detect cantilever deflection towards or away from the surface. By reflecting the ancient beam of the flat top of the cantilever, and cantilever deflection will cause slight changes in the direction of the reflected beam. A position-sensitive photodiode can be used to track these changes. Thus, if an AFM tip passes over a raised surface feature, the resulting cantilever deflection is recorded by the PSPD. And the PSPD stands for Position Sensitive Photo Detector. In this diagram, the detection mode is explained like laser fall on the tip, and the photo detector is detect the change in the sample surface. Next is the imaging mode. In imaging mode, an AFM images the topography of a sample surface by scanning the cantilever over a region of interest. The raised and lowered features on the sample surface influence the deflection of the cantilever, which is monitored by the PSPD. The AFM can generate an accurate topographic map of the surface feature. The AFM has three main abilities: force measurement, topographic imaging, and manipulation. AFM can be used to measure the forces between the sample and the probe. How are force measured? The probe is placed on the end of the cantilever, which one can think of as a spring. The amount of force between the probe and surface is dependent on the spring constant between the probe and the sample surface. This force can be described by using Hooke's law, like F is equal to minus K into X. F is equal to force, K is spring constant, and X is equal to cantilever deflection. If the spring constant of cantilever typically approximates 0.1 to 1 Newton per meter is less than surface, the cantilever bends and the deflection is monitored. Next is what are probes made of? They are generally made up of silicon or silicon nitride. Probes may be coated with other materials for the additional SPM application such as CFM, chemical force microscopy, and MFM, magnetic force microscopy. Why AFM is better than STM? It gives information about the conducting and non-conductive surfaces. 3D images of surface are obtained by the techniques. This technique, the sample can be analyzed in open air. The next is AFM instrument. The main components of an AFM are microscope stage, control electronics, and computer. Microscope stage. Microscope stage, moving AFM tip, sample holder, and force sensor. Control electronics is the second one. Controller electronics, optical microscope, and vibrational controller. Third is a computer. The control electronics usually takes the form of a large box interfaced to both the microscope stage and the computer. Next is the basic concept of AFM instrumentation. The piezoelectric transducer moves the tip over the sample surface. The force transducer senses the force between the tip and the surface, and the feedback control feeds the signal from the force transducer back into the piezoelectric to maintain a fixed force between the tip and the sample. Piezoelectric transducers. Piezoelectric transducers convert electrical potential into mechanical motion. Example of piezoelectric transducer are amorphous lead barium titanate or lead zirconate titanate. A piezoelectric disc will expand readily when a voltage potential is applied. Next is force transducer. It may be constructed that measure forces as low as 10 piconewtons. Next is the force sensor. Force sensor, optical lever sensor. The end of the cantilever bends, the position of the laser spot on the detector changes. As the cantilever detector distance is large, a small movement of the cantilever causes a large change in the laser spot position at the detector. Next is the feedback control. Feedback control is used to maintain a set force between the probe and the sample. In the application of AFM, it can image far more biological processes such as imaging of protein, like any sample like ceramic material, human cells, or individual molecules of DNA. Dispersion of metallic nanoparticles can be imaged. It gives information about the toughness, roughness, and the smoothness value of surface. Application in the field of solid-state physics include the identification of atoms at a surface, the evaluation of interactions between a specific atom and its neighboring atoms. In molecular biology, AFM can be used to study the structure and mechanical properties of protein complexes and assemblies. For example, AFM is used to image microtubules and measure their stiffness. In cellular biology, AFM can be used to attempt to distinguish cancer cells and the normal cells based on a hardness of cells and evaluate interaction between a specific cell and its neighboring cells in a competitive culture system. Soft surfaces are analyzed by this technique without damaging its like lipids. Covalent bond strength is measured by this technique. The next one is advantages and disadvantages. In advantages, there are some advantages of AFM like high resolution capable of 3D measurement with super high magnification. Collected data can be processed. Observation in atmospheric condition is possible, not needing penetrament of sample. Capable of analyzing physical properties like electrical property, magnetic property, friction and viscoelasticity, etc. In disadvantages of AFM, incapable of low magnification and difficulties in positioning due to need to narrow down the field of view. Analysis for each sample takes significant amounts of time, and inability to measure large sample due to the need for penetrament and processing. Relatively difficult operations experience required for cantilever replacement. The last is the limitation. In limitation, AFM can only image a maximum height on the order of 10 to 20 micrometer and a maximum scanning area of about 150 into 150 micrometers. The scanning speed of an AFM is also limitation and highly dependent on AFM probes. That's all from my side. Thank you very much.